to talk about coordination, particularly conditional synchronization. And so this sort of will conclude our a couple lectures on processes and multi-threading in C6. Before doing that, first we start off with talking about the homework. We'll talk a little bit about why we want to do sort of conditional synchronization. There's in many cases that we have seen already in the kernel where like one process wants to wait on another process. For example, the parent wants to wait until the child exits. And there are many conditions like that, and they can be neatly solved with primitives for conditional synchronization. In particular, we're going to look at one particular version of conditional synchronization, sleep and wake up. It's a pretty common one. One that's actually implemented by XV6, and see a little bit how it works. Now, we're going to notice that there are sort of two central challenges in these primitives. One is what we're going to call the lost wake-up problem. Which any of these primitives have to deal with, and then in particular, when you use them in the kernel, there's an interesting action between kill and sleep. So, for example, a process is actually sleeping, waiting on some condition, but some other process actually wants to kill, that particular process, and that results in actually all kinds of complications that, in fact, very few operating systems deal really well with. So that's where we're going to end there. So first, back to the homework. I guess I know why did I? That is weird. No projection. Give me a second to sort this out. Hopefully. Great. I was working a second ago, Mark. All right, good. Back in business. Okay, so the homework was looking at user-level threading, correct? So we looked at last week in lecture at how the kernel switches threads, but turns out this thread switching mechanism is a general purpose actually idea, and you can apply the same idea in user space. So you can take a single thread in user space and basically turn it effectively into multiple threads. Right, and the homework is basically looking actually in how to do that. And if you noticed, the solution, the actual solution is pretty similar actually to what XV6 internally does. So this is sort of a generic idea for how to do thread switching. So just before we dive into the actual solution, here was the little program called thread init to initialize the thread package. It creates two threads, both called myThread, and then it's called thread schedule. Right? And the intention is that we're going to be switching back and forth between those two threads called myThread. The two myThreads are very boring. You know, they're just saying I'm running, and the next thing they do is they actually yield the processor or the current thread to some other thread, right? And so our scheduler is in charge, or package in charge, to make sure that the other thread runs. So let's first look quickly at creation, because that's sort of an important part. So in create, what the creation function does, you know, it looks for some thread structure, correct, that's declared at the top of the file, and then it finds a free one and initializes it. And the main interesting action is all around what actually happens to the stack, right? So we have our stack going down, then what it starts at doing actually sets the SP, the thread stack pointer, top, and then basically goes off and initializing the stack. Right? In a very similar way that we've seen inside of x86. And so the thing that it does, the first thing it does, it actually lowers the stack by 4, and it actually puts the address of the function on that location. So it puts the address of the function down. What's the purpose of that? Why put the must have seen this doing the thread switching code. Why put the function there? Yeah, we're going to use the red instruction to switch between threads, and the red instruction, what it does, it captures, it pops the EIP, correct, for where to return from the stack. And so at some point we want to run this thread, and this thread should start in the function func, right? And we're actually, in this case, my thread, and so we're going to put the EIP here in the top of the stack, so that at some point when we do the switch and we do the return, then we'll actually return to this function. So then it does a bunch of other things, and actually mostly quite boring. The only thing, actually, the other thing it does, it actually allocates some space in the stack. So it subtracts, when it's 32 entries, bytes on the stack. And presumably what's going to happen with those entries is, of course, this is where we're going to pop off the registers that normally are stored on the stack and that we're using to that we need to save and restore on the thread switch. Because this is the first thing we create, there are actually no saved registers at this particular point in time, and so we're just initializing effectively it all to zeros. Right? And so 8 registers times 4 bytes is 32 bytes that we need to do, and then we set the thing to runnable, and by setting it to runnable, presumably the scheduler knows that should pick up this thread. Right? So let's look at. Let's go up and quickly look at the thread scheduler, which is incredibly boring. It just runs through all the threads, finds if there's a thread that's runnable, sets, if it is the case, it sets the next thread, to that next thread to be run, which just happens here, and then the next thread is 0. That means there were no runnable threads at all. It just panics, which is not what a typical thread package will do, but it's good enough for our homework assignment. And then if there is something to be run, then we set the thread state to running, and we call thread switch. Right? And thread switch is this piece of assembly that will actually do the switching. Right? And so I'm presuming you all figured this out, but just to make sure that we have the same solutions. Yes. Let's see that again. A little bit larger. So here's the actual thread switch. So we're going to go from one stack to another stack, correct? So this is the one that say a target thread. This is the thread where we're switching from. We has a stack 2. And the first thing we do, of course, is save all the states for the current thread, right? And something interesting already happened, correct? Because what happened when we called thread switch? What value you get? Yeah, so the EIP, in some sense, already has been saved, right? Because when we call thread switch, the x86 instruction for call will save or push the EIP of where to return on the stack. So one crucial piece of information that we need later on to return is already there. And while that happens to be, not in exactly the same place where we initialized our func address. Okay, so when then the next thing happens, we're moving ESP into EAX. What does this do? Well, this has to do a lot with like what the layout or the structure of these thread structures are. If you look carefully in the thread structure per thread, there was at the bottom of the thread structure is the stack pointer, the safe stack pointer. And so presumably what we're doing, we're moving ESP into this value, we just had here, into the stack pointer register. Then we remove, oops, I skipped one step here. We did first do a push all, correct? So after the EIP, we do a push all. So what does push all do?
Pushes all its other
Pushes all the general purpose registers, the 8 registers that we expect here. So here's going to be, and how many bytes is that going to be?
32.
32 bytes. Yeah. That's seen this too many times now. So the step point is pointing here. So what we say in correcting this structure is actually the address of the last thing that we pushed. Okay. So then we'll switch actually threads, right? Which is the we're going to move EAX into EA. We take next thread, correct, which is the thread that we're going to run next. At the bottom of next thread is going to be its safe stack pointer, right? Which in this case, it's going to be pointing to here. Right? And so we're putting the safe stack pointer into the stack pointer register. We actually initialize next thread to 0. That has to be maintained some invariant, correct, in the thread scheduler. And then we do a pop all. So what's the pop all going to do? It's going to pop all these 32, the 8 registers, correct, into the machines or the processing registers. There are 8 zeros in this particular case, and so all those registers set to 0. And then, so that clears up this part of the stack, right? And then the next instruction is the red instruction. And voila, that should return us exactly to the following, right? Everybody clear on this? So this is very, very similar, correct, to all the other thread switching mechanisms that we've seen, and just the main point of this homework assignment is actually for you to do it once in user space and to see that it actually is exactly the same idea. And give you more exposure to this whole thread switching, which, as we talked last time about, it looks a little bit like magic the first time you see it. But when you do it a couple times, you actually get a good understanding of what actually is going on. Everybody happy with the solutions? Of course, you'll probably also notice you could have gotten this wrong in all kinds of interesting ways, and things didn't work out. I mean, you have to be very, very careful, correct? I mean, the order of the instructions and the exact instructions are crucial to actually get this to work, like many of the OS code that you're writing, right? The details matter a lot. Okay, there's a couple more things that I wanted to ask. So the homework asked for a particular address, right? Which I think the address here was 161 OS. I was on the stack and asked you what does this 161 refer to? Given the explanation I've just given, it should be straightforward. What's 161? So the return address of which particular? Did anybody sort of look up? You can usually find it out, but if you do ufred.asm, you can just look for 161, and you'll find that it was my thread, right? Which makes sense, right? It's the address corresponding to my thread. Okay, a couple more interesting things that we can ask. This thread package is incredibly dumb and not particularly good. So, for example, one interesting thing that happens, so let's say one thread in the user level, we have three threads running, correct? And one of these threads actually does a system call, and that system call blocks in the kernel. What happens to the other threads in that user level program? Huh? They stall too, right? Because the user level thread scheduler has no idea that that thread happens to be blocked inside of the kernel, right? And this is a standard problem that often shows up where you write a user level thread package. So we have the user space process with the kernel. The kernel has its own set of threads. And in the case of x86, for every kernel, for every user level thread, there's a kernel thread. But then on top of this, user level thread, you implement it, or uthreads implements, scheduler that implements its own set of threads. Right? sort of like recursively applying the same ID over and over. Right? And we could go further. Right? We could put the scheduler on top of this view of the thread and implement another thread scheduler if we wanted to. And so the problem now, we have, let's say, if one of these guys goes into the kernel, correct, and blocks, and this guy's sleeping heavily, this scheduler knows nothing about that this guy is sleeping because the only scheduler that knows about it is the kernel scheduler. So how can you solve this problem? People know what operating systems like Linux do, or
just avoid blocking kernels.
All right, that'll be one solution, correct? Have no calls in the kernel that block, which work really well with Josh. The ones we implement in labs, right? Because none of the system calls in Josh actually do block in the kernel. It's one of the great features of Josh. Unfortunately, many other operating systems don't look like Josh at all. More look like XV6. And so they have a different plan.
Support threads at the kernel level?
Sir?
Support threads at the kernel level?
Yeah, well, we have threads at the kernel level, right?
Have user threads map one-to-one to OS?
Yeah, or that one solution, which actually Linux uses, and these user level threads actually corresponds to a real thread. And so instead of like this picture, really what the picture is. So when one of these threads actually blocks, then the kernel will schedule maybe one of the other user level threads in that process, and that will work because it will have a corresponding kernel thread. Downside of that is, of course, that there's a bit of overhead now, right? Because for every user level thread you create, you also have to create sort of a full process, a full kernel thread. Any other ideas about how you might solve this?
You have syscalls which return if they're not able to execute at that time, so like one instruction before the syscall, or directly after the syscall, so it calls it again.
Yeah. You can change all the system calls or all the blocking system calls that are basically return the code saying like, hey, I'm going to block. Check in later with me whether your operation actually succeeded. Whether the networking system calls do that. There's another way of getting around this.
You could also use a hybrid threading model where you have M user threads correspond to N kernel threads.
Say again?
You can have a hybrid threading model where you have two user threads correspond to one kernel thread.
Yeah, so good. So let's say you're gonna, instead of having, we have many of those guys, but we maybe have two sort of threads that interact with have corresponding OS threads. And how are we going to use the second thread?
Well, so that the two OS threads can run any two of the user threads.
All right, but then if you have three you blocked, then you run out, right? So you can actually use this thread. This is a trick called schedule activations. You can use the second thread to basically do half when the operating system blocks these schedules a thread. It could make an up call to the user level thread packet saying, hey, I'm going to block one of your threads. You better do something if you want to do want to run in another thread. And you can, for example, use that second thread for actually doing the up calls. There's an idea, it's called schedule activations. And in fact, you can think about what you're implementing in JAWS in Lab 4. Actually, you will do up calls, right? And you can think about those up calls as scheduler activations. Right? Make sense? Scheduler activation actually is a very clean idea. It's a pretty old idea by now, but only recently, I think, for example, Windows actually incorporated it as a way of doing user level thread scheduling. Any further questions about this? We're all good? All right. All right, so back to the main topic of today, which is going to be synchronization. So just to make sure that we have the right picture in our head again, so the problem that we're going to be focusing on is we have N kernel threads. They share data structures, that we see all the time. So, for example, they might share the proc table. The data structure from this last lecture, and actually the previous lecture too, I believe. And we know that to protect, make sure that operations on the proc table happen atomically. We use locks to implement critical sections. Right? So the sequence instructions can updates a particular entry, for example, in the prop table atomically without other threads interfering. Right? Now, so that's one type of synchronization or coordination that you need to do to make sure that, like, the invariants are maintained across the process structure. Now, the second thing that shows up a lot is that some thread needs to wait on another thread. And we've seen this in a couple of cases. We have seen a parent waiting on a child. And so where one thread, forks up another thread, then that, the parent thread wants to wait until actually the child thread exits. And so there has to be some plan where that parent can actually wait, for the child process to exit. We have a similar thing what we saw is where we were waiting for the disk interrupt. For example, in the IDE driver that we looked at, one thread will start disk operation because disk operations are slow as a magnetic disk, and then the process goes to sleep, and the job of the IDE interrupt handler was to wake up the process when actually the write disk block has come into memory. Right? So that's another form where we're doing sort of this conditional synchronization when one thread is waiting on something else to get done. In this particular case, it's waiting for an interrupt to be delivered. Any other examples that you can recall from XV6 that have sort of this structure of somebody's waiting for somebody else or needs to wait for somebody else? No other examples that come to mind? So there are a couple, in fact, if you look at the source code carefully, right, there's a whole bunch of places where this happens. So for example, another one is in type read or type write. There are two cases. One thread reads for a pipe, but there's nothing in the pipe yet. Then it needs to wait until the writer actually writes something into the pipe. Right? So this is a classic example of sequence coordination. Like you look in any intro textbook, they'll talk about this, bounded producer-consumer problems where like one thread produces, the other thread consumes, and if there's nothing to consume, you have to wait until the producer actually produces. Right? So this is a common problem. We'll look at that in a second, of course, because you have to implement pipes. You will have to deal with this issue too. In fact, if you're looking for the source code, this is like many examples of this kind of interaction. Okay, so and then this kind of interaction goes by different terminology. Some people call it conditional synchronization. Sometimes it goes by the word of sequence coordination. In 6033, it often talks about sequence coordination. And it's sort of a classic concurrency problem. It's slightly different from the problem that Locke tries to solve, and so it has its own set of solutions. Yeah, right.
Is the parent waiting on the child different from the pipe read in that the parent has to wait for the child to completely finish?
No, they're basically the same. They're slightly different. Okay, the way to think about it is all they're waiting for some condition to become true. Okay. And the condition that needs to become true is different in the two cases, but they're all of the same form, and we'll see that in a little more detail in a second. So how can you solve this? How do you sort of implement conditional synchronization? Well, the simplest thing to do, correct, is if you're waiting for a condition for the child to, for example, to exit, you can just spin, correct? You just check the XV6 proc structure has a piece of information that says that the child actually has exited, or its state has been changed to zombie, or you can just spin in that field, correct? It's like I'm waiting for you to exit. I can just spin on your proc state field and wait until that proc state field turns into zombie, and I know that at this point you're done. Right? So in general, I could do that. And almost for everything, I could do that. Correct? For example, with the pipe case, there's going to be some variable that counts the number of bytes in the pipe, and if I'm a reader, I can just wait and spin until that variable changes content from 0 to a positive value, so there's actually something for me to read. That seems like an easy solution. So the question is, why does this lecture stop right here and actually has more to it?
Wastes a lot of resources.
Yeah, it wastes resources, right? If you have only one processor, for example, then the guy that actually needs to fill the pipe might never run because you're spinning. Right? So that would be slightly undesirable. And so you need a way of actually releasing the processor so that actually somebody else can actually fulfill the condition. Right? Even if you had like a lot of cores or a lot of threads, it's probably still a waste of cycles. Right? You could probably use that processor to do something more useful for some other thread instead of having that one guy spin around. Yeah, go ahead.
So, is there a reason we don't wait on locks then? Why don't we just say, I'm waiting for this lock to be undone, and then whoever a signal for you to give
So it's a good question, right? Like so the question goes back to like the implementation of locks that you've seen, correct? And when Robert lectured about locks, he described spin locks, right? Where the spin lock actually sits to spin around, waiting until the other guy releases the lock, correct? And I think your question is like, why not? If it's good there, why not good here? Correct? That's a very good question. So why is it good there? Why is it okay for spin locks to spin and not the release of processor?
Whenever they're used in operating systems, they're only acquired for a very short time and then released. They're not blocking an IO or things like that.
Yeah.
Locks that would block an IO would actually yield.
Yeah, so this is the right answer. In all the critical sections that you've seen in x86 and the ones you've seen in JAWS are few instructions. And so it's perfectly fine for the person who's waiting for the lock to spin in that lock because he knows he's going to get it very, very soon. In fact, he's going to get it in a couple of instructions probably. And while in these cases, this is not the case, right? I mean, before the child exits, whatever, it might be computing some, nth digit of pi, and it will take a long, long time before actually you will release the processor. And so spinning for that long period of time would be very wasteful. While spinning for a few instructions, it's hard to do better, right? Because you're going to take some time to let you go to sleep, and that's going to take some machinery too. So that's a good. So, and also, as you point out, there are versions of locks that they're called sleeping locks, where the thread might spin for a little while and then go to sleep if it's spinning for a long period of time. In x86, we don't use them. We either use spinning locks or we use conditional synchronization. Right? Good question. So back to these cases, we do want to actually have some solution for this. Right? We want to be able to release the processor so that somebody else actually can do the work. And it turns out there's a whole literature. As I said, this is a classic synchronization problem or concurrency problem. There's a whole literature with proposals for primitives to implement conditional synchronization. And you will see a couple of them in either in this lecture and in the next homework. So, some condition variables, which we'll use in the homework for next week, as a form of conditional synchronization. Semaphores, you might have heard of, is a form of conditional synchronization. We'll talk a little bit about that. The primitive that we're going to be looking at is sleep and Wakeup. The x86 way of doing conditional synchronization. Okay. So in the x86 instance, the sleep takes two parameters or two arguments. One is what we call a channel. It really is nothing else than an address, and it takes a lock as argument. We'll see the second Y, and then Wakeup takes the channel as arguments. And so the intended style is we have one thread running, we have another thread running. The thread will test some condition. For example, are there buffer? Is there bytes in the pipe that I can read? if the condition is true, it just proceeds. If the condition is no, then it goes to sleep. And then at some point in time, maybe another thread, will put some bytes into the pipe, and it actually will call Wakeup to alert, the destination thread, the threads that might be spinning or waiting on this, not spinning, but waiting on this, to tell them that they can wake up. And so we need to have some way, since there might be many, many different conditions under which threads are waiting for, we need to basically name for which thing they're actually waiting for. And this is like in x86 uses this notion of a channel, which is just a variable in address in memory. And other ways you can name the condition on which this particular thread might be waiting on. So this is the channel. Now, the protocol in many of these primitives is that when you do Wakeup, you wake up all threads that are actually sleeping on this. So you might have a case where you have multiple threads sleeping on this particular channel, waiting actually if there is any input. For example, you might have multiple readers on the same pipe, right, all waiting to read some bytes. Then when the producer comes along and sticks one byte into the pipe, in x86, when you do a Wakeup, all threads that actually are sleeping on that channel will be woken up. Of course, that doesn't mean that they all should run, right? Because there's only one byte in the pipe. Right? So typically, the way you see this always organized is that when you come out of the sleep, the thread actually tests the condition again. And presumably one of them is going to get lucky, get the one byte, and proceed. All the other ones, are going to test the condition, find there's actually no bytes in the pipe at all, and go back to sleep. Does that make sense? So in fact, you see in x86, and this is a standard thing to do amongst all on all conditional synchronization, is that you see a loop around that actually tests the actual condition, the thread-specific condition on which they're waiting for. Yeah.
What prevents a massive race condition once everybody wakes up, so that they don't all?
So here's where the interesting part comes in. There's an interaction between locks and conditional synchronization. And so what really happens, correct, is that to test the condition, we have multiple threads testing the same condition. It should be only one who actually holds the lock to actually test that condition. Right? So presumably, typically what actually happens, you do an acquire first, from some lock. Okay? You test the condition, and then you go to sleep. Now, if you go to sleep while holding the lock, is that a good situation? No, it's not such a good situation, right? And so you should at least release the lock before going to sleep. Now, the way it works in x86, in almost all condition variables, actually you pass the lock that you're sleeping or that you're holding, you pass it actually to sleep. And I'll talk about that in a second. This is a crucial point. And then the protocol is that when you come out of sleep, you come out of sleep while holding the lock. So Wakeup will wake up a bunch of threads. They're all trying to get the lock. Only one will get the actual lock. It will come out and we'll test the condition. It will test the condition. Either proceed and be done and release the lock, correct? And then the next thread who is waiting on the lock will get the lock, go test the condition, find that the condition is not true anymore, and goes back to sleep. All right? So, the interesting question really that needs to be asked, why, the lock is an argument to sleep. And in fact, that's basically where most of the action is. So let's first actually look in a little bit more detail what actually goes on in sleep and wake up. So here's the sleep implementation in x86. Okay, here's the arguments, correct, the channel, and spin lock as argument. Nothing particularly surprising. And then when we get into sleep, the first thing the sleeper does is actually acquires a lock on the process table. And we expect that it would acquire a lock on the process table, of course, because it wants to change its state from running to sleeping. So it needs to update some structure in the prop table. And so need to get the lock on the proc table, correct? In the same way we've seen before, that when threads make a change to the proc table, they need to take a lock out of it, because what happens, correct? Other threads might be looking, a scheduler thread might be running through the proc table looking for threads to run, and we want to make sure that this guy finishes its operation, go to sleep before a thread scheduler actually looks at it. And then it actually releases lock. And so we'll come back to it in a second. The order between these two statements is crucial. In fact, if you turn it around, you do the acquire after the release, basically we have a big problem. And we'll talk about that in a second. But just to alert you for that. Okay, so let's see how you could use this, right? And let's look at IDE as a good place to look. So here's IDE, correct? IDE, this is exactly as before. It acquires the IDE lock, right? The reason it acquires the IDE lock because it's going to look at some shared data structures that other threads might be changing, particularly the queue of outstanding disk writes. And then here it tests some condition, right? Some disk driver specific condition. If the condition is not true, it goes to sleep on a channel. In this case, the channel that corresponds to the address of the buffer. And it passes the IDE lock to the sleep primitive. So the protocol is that when sleep returns, correct, it will have the IDE lock in its hand, acquired and all, and it goes back to the top of the loop, and we'll look at the condition. Okay? So this is how you use things. So let's go back to, and so let's just see a little bit of what sleep does else. It grabs the key table lock. It actually goes to sleep, and it knows basically the channel on which it's sleeping. Right? And this is just basically a number, if you will. It sets its state to sleeping so that the scheduler won't pick it or choose it to run. And then it's called sketch, and sketch does the same thing that we saw last week. It goes off and finds some runnable thread to run instead of this one. Very similar to the user level thread package, correct, that you implement. So the interesting question is, so what happens in Wakeup? Well, Wakeup is pretty straightforward. It grabs to the P table lock. It has to because it's going to look at the state variable, correct? And it calls Wakeup, and Wakeup, is very straightforward. Runs through the proc table, looks for a process that is sleeping, and it looks for a process that is actually sleeping in that specific channel for which the Wakeup is coming for. And if so, it just turns into runnable. Right? And so at some point in time, the scheduler is now going to run this thread, and it runs that thread. It will come out as get, correct, as we saw before last week, and then it sets its channel to 0, and then it actually releases the P table lock, and it grabs then the lock, the higher level lock, correct? In the case of the IDE drivers, would be the IDE lock. So this way it returns out of sleep, correct, holding the lock. All make sense?
So this happens with the program itself, is that Wakeup won't be lock for you.
Sorry?
Wakeup won't be grab lock for you.
Oh, well, the sleep will grab it for you, correct? You get when you come out of sleep, you will hold the IDE lock again, in the case of the IDE driver. And sleep does it for you. Okay, so now the key problem is this is understanding why sleep actually, let me see this. The key problem is one of the interesting points in terms of understanding why sleep takes an IDE lock is by trying to, one way to understand that is to figure out what happens if sleep didn't take the IDE lock. Well, clearly it has to be the case that the lock needs to be released, because otherwise nobody else could update the data structures that you're waiting on, right? So one option is to say, well, we're going to change sleep, and what we'll do right before sleep, we'll just release the lock, and then we call sleep. And is that a good idea? Presumably it isn't, because otherwise, because it seems a little bit unclean, correct? Why would the sleep need to know about the lock that is held by, so it seems the internals of sleep needs to know what the thread it's calling actually holds a lock. So why is that the case? Now we can investigate that, since you don't want to think too hard. That's always good. So the way you not to think too hard, correct, is to change the code and see what goes wrong. So one way to do that is to actually release this lock before doing that acquire, correct? Because that means that it's the sort of the equivalent of like calling release right before calling sleep, correct? And so presumably something bad happens if we do this. So let's do this. Hopefully I can get lucky. Please be lucky. Looks like I'm lucky, or unlucky, whatever you want to call it. There's no shell, right? And so let's, just make sure that, I'm not doing something bad. Let's turn it back and just make sure now things do work. Because so hopefully now things do work. They do. Right? So, we change this one line, correct, and something bad happens. And so what's the problem? Yeah, you can miss wake-ups, correct? And this is a classic problem with condition variable or condition synchronization primitives. And let's see actually quickly what happened in this particular case. So let's say we're running back, we're in the IDE again, and we do IDE read write. Just this code we just saw, correct? So this guy grabs the IDE log, tests the condition, and then goes to sleep. But in this case, where the IDE lock is released before acquiring the process table lock. So what could happen? Well, the point that we released the lock, remember in x36, what was enabled when you release the locks? Interrupts, correct, or enabled. Now this guy, presumably before he went to sleep, actually kicked off a disk write, correct, or a disk read. Now that is in progress, and it might be the case that at the point that actually releases the lock, that actually disk write is ready to be served. So in fact, what could happen is that at this point, like the IDE interrupt handler might run, correct? And the IDE interrupt handler will grab the IDE lock, because right before this guy we did the release, correct? So in between the IDE interrupt handler runs, it grabs the IDE lock, and then it does a wake up. And then it returns, and it's done, correct? And releases the IDE lock. So this all happens just between these two instructions, correct? Then, our IDE read write thread actually goes to call sleep. It will set the state to sleeping, and it will happily sleep forever, right? Because there's no interrupt is going to come along anymore that actually will wake up that particular thread. Now, maybe somewhat later, another disk interrupt happens to come along, and it will wake this guy up, but there's no guarantee. Okay? And so. So clearly, it has to be the case that we cannot release the lock before we acquire the p-table lock. So this is wrong, because that basically allows exactly this race to happen, and you get the lost wake up. This is called the lost wake up problem. Make sense? Okay, so now we need to understand why, if we do it this way, there's no possibility of a lost wake up. Yeah, go ahead.
I think you're modifying the wrong code. I think that's the
there's the bottom end. I don't want to do that. So I want to modify this. So thank you. So this is, oops. Change my key bindings. Yeah, I'm back to the right place. So this code is correct. Right? It requires the p-table lock before does the release of the lock. And we've seen if we change these two statements the other way around, things go wrong, we have a lost wake-up problem. So the only thing now we're left for us to do is convince ourselves that if we do the release after acquiring the p-table lock, we never have the lost wake-up problem that we talked about. And so, can this race that we have here on the board, can that actually happen if we so why is this code correct? Yeah, right.
So Wakeup also requires the table, so you require it before you release that lock.
Correct. That's exactly right. Wakeup actually requires the p-table lock. It has to because it's going to look at the proc table. And so if we hold the p-table lock, if we grab the p-table lock before we do the release of the IDE lock, right, there's no way that the IDE interrupt can actually get in there. Right, so what the scenario now is going to be, we have our thread, we have our other thread, so this is going to go to sleep. It's going to grab the p-table lock first. And then it's going to do release the IDE lock. So at the release of the IDE lock, interrupts get enabled. The interrupt, some other thread actually gets serves this IDE interrupt. It will call Wakeup. The Wakeup now wants to grab the p-table lock. It won't be able to grab the p-table lock because actually the thread that is going to sleep already holds it. Right? So it's going to grab the p-table lock, or try to take the p-table lock, but it won't have, it won't succeed. It will actually wait. It will spin. Right? Well, while it's spinning, actually this is yeah. So while it's spinning, the other guy will now release the IDE lock. That'll be perfectly fine, nothing wrong with that. And this guy will proceed to actually puts itself first to sleep. Right? And it only releases the p-table lock until it has put itself to sleep. So the points, so at that point, the state is set to sleeping. Then it releases the p-table lock. At that point, this guy gets to run. Right? But now, when it runs, the state actually stands to sleeping, and it will actually wake up the process again. And so the race that the lost wake-up problem is gone. And so this is the crucial reason why sleep takes an extra argument, namely that lock. Because naively, like if you do this for the first time around, you would say, oh, I don't really have to pass this lock argument to the sleep. Why should sleep or the thread scheduler know about which locks I'm holding? And it's exactly for this reason that the sleep actually takes this extra argument. Yeah, go ahead.
So is there a reason the lock is reacquired before returning to sleep? Is it just programmer convenience, or?
Yeah, that's programmer convenience.
Because one could imagine a situation where it's sufficient to just read the condition variable with acquired consistency.
Yeah, but just to make it symmetric, sleep returns with the lock in its hand. Yeah.
So what if you're holding like 5 locks?
That's the right question to ask. So what happens if you hold 5 locks? Should we have like a sleep with 1 lock, sleep with 2 locks, sleep with 3 locks, sleep with 4 locks? What's the answer to this question?
With another lock.
You set up a new lock that stands for I'm
holding 5
releasing all of these 5 locks. So you acquire the new lock, release the 5 locks, and then call sleep on that.
Yeah. So that'll be one way of doing it. But basically, it really indicates that you have a bad program. Right? You should not be writing code like that. So this encourages you at least to do the right thing. But if you wanted to write that code for holding 5 locks and go to sleep, then you're forced to basically have another lock that surrounds the 5 locks. And then you acquire first before you release those 5, and then you go to sleep. Yeah?
This does be kind of dangerous to acquire any lock while you're holding the p-table lock, because of the ordering.
Yeah.
This is like the p-table is almost always the second lock you grab.
Yeah. So this comes back to, I don't know, Robin talked about this last time, lock ordering. If you acquire multiple locks, you better be very, very careful. Right? And one rule you should follow in life is always acquire them in the same order. And this is a standard rule to avoid deadlock. Because if you one did them in one order, the other in the opposite order, right, you could easily get a deadlock. Yeah. still tricky to write correct code. But at least, by passing lock to sleep as an additional argument, he actually can get this code correct. So given now you understand the sleep wake up problem, are there other ways of solving this problem? So one way, of course, is to do this trick where you pass the lock to the sleep call. Are there other ways of you can imagine solving this problem?
Turn off interrupts. You could turn off interrupts so that you don't trigger one, right?
I guess you could turn off interrupts. No programming with interrupts. That's sort of saying like no programming with locks.
Yeah.
That would solve that problem too. Any other ways you could do this? So remember, right, the problem was that the guy actually did a wake up before the other thread actually went to sleep. So one way to solve this problem is to make sure that that just not can happen, right? Which is basically what our sleep wake up problem solution does. What's another way to do it?
I'm not totally sure if this is correct, but maybe we could set the state to sleep before releasing the IDE lock and then not worry about it while you go.
That will probably break other invariants, correct? Because there's lots of other code looking at the proc table, so you should really, there isn't an invariant of the proc table that you have to hold.
Unless you could make it lock free.
Okay, so again, there may be ways of making it lock free, but we want to stay in the locking paradigm for now.
You make it so that sleep would immediately return when that wake up if the condition is already been.
Yeah, so how could you do that?
You gotta put a flag that anyone. Sure.
Is a flag sufficient? Is a flag sufficient, or?
And imagine you need a little more for that.
Yeah, that's a good idea. So if we can go in the direction.
Might be like a queue of wake ups.
Yeah, or how about just a counter? Just counts the number of wake-ups, correct? And so when sleep goes to sleep, checks if this counter is bigger than zero. If it's bigger than zero, it means, somebody already did a wake-up, and I should just decrease the counter by 1 and go back out. Okay. So just reinvented semaphores. Another classic conditional synchronization primitive that works exactly like that way. So instead of actually passing the lock to sleep, you basically have a counter. It's called a semaphore that counts the number of sleeps and wake-ups. Make sense? Okay, good. So that's one problem, right? I promised you there was a second challenge. And the second challenge has to do with killing processes or threads. Just to review that a little bit. And actually, this turned out to be sort of nasty. Review. Okay, so remember, system call right to kill a process ID. And the intention is that let's say, for example, some process in an infinite loop, correct? Then another process like the shell, you should be able to actually kill that process. And so that's why kill is there. And there's sort of two. We've seen how kill is generally implemented, correct? But there's two central challenges. When you do a kill, problem number one. So one thread tries to kill another thread. Problem number one is that actual thread might be running. And so the thread that actually is the target to be killed might actually be running on the processor. And would it be okay for us to just blow away, like if you're the source and you want to kill the target thread, and the target thread is running on CPU 1, you're running on CPU 2, I just want to blow away, the thread on CPU 1. Does that seem like a good idea? Like, how would you make it work? Well, what are things that could go wrong? Maybe that's a better way of thinking about it.
What if the process you're killing is in the middle of a file system update or something? Leaves it in an inconsistent state?
Yeah, it might be in the kernel, correct? And doing something crucial. It might be holding locks. Or it might be in user space and holding locks that other user level threads care about, right? So that seems very, very dangerous, right? Because to kill some process in the middle while it's running on the processor. You probably should kill it only at particular points in time. Right? And so the way this problem is solved, in general, is pretty straightforward. The target of the source, actually doesn't kill the process directly, but what it just says, drafts the p-table lock and says, whatever, the target for that prox entry, x86 and go to 1. And And that's all that happens. And so now, of course, there must be another corresponding piece of code that checks where the pklt is set. So where would you expect a piece of code that actually looks where the pklt is set? Scheduler, maybe. That's a little bit dangerous. We have seen it actually before. Let me first let's first look at kill, and then you see how simple it actually is. Here's kill, right? It does exactly what I said, and he just sets the p state to kill, and that's it. And in fact, we'll talk about this the second two lines a little bit later. But let's go back to trap. And so there was this sequence of code, correct? So periodically, correct, the user level program will go enter the kernel because it will get a time interrupt, correct? And so this thread that is running on this other processor that we're trying to kill, at some point it will will enter the kernel because it made a system call, or it will be forced to enter the kernel, correct, to actually release the thread because it runs out of its time slice. So in either case, it's going to come back through, when it wants to return back to user space, it will check this proc kill flag, and then basically commit suicide. Right? Because so what the plan that we're hearing is, instead of actually forcing a process to kill, instead of blowing a process out of the water, we actually allow the target process to actually clean up itself. And that's good because the point, the process can actually release everything that needs to be. The kernel can make sure that it actually cleans up in a good state. Right? Yeah. Right.
Why is doing it in the scheduler somewhat dangerous?
Because we need to make sure that the target process, the target thread, is actually off the processor and definitely not running, or not intending to do anything here. So at this point, we know exactly what the target process is. It's about to return to user space. It's done in the kernel, so there's no state anymore in the kernel that it actually no locks that it's holding. It's in a perfect position to actually get killed, okay, just before returning to user space. Right? And so that's exactly what it does, and exit does then the usual so exit then does the actual cleanup, it releases, closes all the file descriptors that it has open, releases the current work directory, reference count, and then basically informs its parent, that it's dead. All right? So that takes care of one big problem. Right? So the problem of that, if the target is running on the processor, the way we solve that is basically by forcing the target to commit suicide at some point later. It might not happen immediately, but at some point later, it will be cleaned itself up. Now the second problem is what happens if the process actually, the target is sleeping. And this is a little bit more tricky. Right, so now we're in a situation where the target process is actually somewhere in the kernel and is sleeping somewhere in the kernel. It's probably not holding any locks, right? Because when you go to sleep, you release that one lock that you're holding, and so it just sits there somewhere in the thread scheduler queue, sleeping. But we need to get it out of the kernel. Basically, we need to make sure do something. So one option is to say, well, it's actually not running, correct? It's sleeping. We just turn the proc structure and clean it up. It will never run again. And so, and then we're done. So how hard is that? Why is that not? It's not a good solution.
What if someone's waiting on that one? If someone's waiting on that?
Maybe somebody's waiting, or maybe itself is waiting on something. And actually, it's important. For example, it's in the, let's say it's in the create system call, and it's reading and writing, multiple disk blocks. It went to sleep reading the first disk block that it wants to update, and but as part of the create system call, you need to update maybe 2 disk blocks, maybe like the free inode list or the free disk block and the block that you're going to stick in your inode. Right, so you have to do 2 disk writes. If you would just remove the kernel thread, like in the middle between these 2 disk writes, would that be a good situation? Not really, correct? Because you would have allocated a block, but not recorded that you're actually sticking the block in any inode. So it's actually bad to basically, take a thread that is somewhere in the kernel sleeping and just remove it. Right? It might be part of a multi-sequence step, and we need to make sure that we actually execute the full step, and we can't just blow it out in the water. That make sense? Okay, so, but it'd be bad actually to do nothing, right? Because that means that that kernel thread might never know that it actually got killed. And so what actually XV6 does, it sets the P killed and it does then a wake up. And so in some cases, for example, in console, let's say you're reading on input from the keyboard. The console read, correct, is the function that reads from the keyboard. And notice here, here's the sleep, correct, with this lock. So at some point when you do a wake up, as part of the kill, it does a wake up, it will loop around, and then the next thing it does, it actually calls it checks if proc killed is set. If proc killed is set, then it actually releases the lock and returns -1, indicating that the system call got interrupted. Right? And so in this case, it's perfectly fine to do that, correct? Because there's no multi-step operation going on. It's perfectly fine to basically check that kill flag out of the sleep and blow out of the kernel. Now, how about in IDE? Is there a similar? We'll get the wake up, correct? But there's no checking for flags here where P killed is. There's no. We're not checking where the P killed is set, right? And so we're immediately going to go to sleep again. Does that make sense? And so the reason to do that, why P killed is not checked, correct, is because this disk read could be part of this multi-step operation, part of the file system, right? That I can create a file, you have to write multiple disk blocks, and we allocate one disk block, and now we need to update the inode. We in between decide we're going to bail out of that system call. That would not be a good thing. Right? We cannot sort of, And the other example was a very simple system call where we knew it was perfectly fine to bail out of it immediately after that sleep. Here we're in the bowels of the kernel somewhere deep, correct? We don't really know which system call we're actually, as part of which system call this read and write happened, and we can't just bail out, right? Because it will break invariance. Yeah.
Why is it okay to exit after the interrupt handler? Because couldn't you have just gotten your timer interrupt and you're just still in the middle of something?
Which exit are you talking? Sorry.
Sorry, it's in the trap handler.
Yeah.
When we actually call exit to kill the process.
Yeah.
So couldn't you have been handling a timer interrupt in which case you're still in the middle of something?
Remember, like at the end of the trap handler, we're about to go to user space. So we're done with anything that happened in the kernel. At least the current thread doesn't really care anymore what happened in the kernel. An interrupt might be coming in, and it will be surfaced, but the thread that's about to return to user space is not holding any locks anymore. It is clean and about to go out. That's perfectly fine to take it there. Right? It's at the end of the system call. It's not in the middle of the system call, so there's no invariants that are going to be broken. While this sleep is in the the bowels of deep in the kernel, and it could break all kinds of invariants. Yeah.
So does this make it possible to write like an application where, like, say you write something that doesn't check for killed, and you just sleep, like you say do that now when you sleep and you wake up, does that mean that your program cannot be killed?
Yeah, it seems like the program can't get out to kill. Right? So in fact, this brings me an interesting issue. Like, what is the spec of kill? What does kill mean? And so the XV6 spec, which is a little bit of basically has a cop out. Where kill, really what kill means is spec basically for kill. There's no formal spec of kill, correct? It's like if there were to write down the spec of kill, what the specification of kill in XV6 is if you're in user space, you will be killed. If you're in a kernel, You might be killed. Another way of phrasing this spec is to say, it's guaranteed that after a kill, you will never execute, the target will never execute any user level instruction. It might execute many, many kernel instructions, but never, never a user level instruction. Right? And that's your sort of the answer to your question.
Because you can't return back out in user space.
Yeah. You will never return to user space. You will never execute a user instruction again. But you might be in the kernel for a long period of time. Now, and will, correct, at some point, this loop will terminate, right? Because the disk interrupt will be completing and it will do a wake up. But it may take a long, long time, correct, for that process actually disappears. Now, you can imagine all kinds of schemes to do better than that, right? Where basically what your only goal in life is to make sure when you target some process to be killed, you want to kill it as fast as possible. You don't want to delay it for any particular point in time because this code might delay it quite a bit. Right? And so, many operating systems should try to do better than XV6, but there's always corner cases where they don't really do a good job. So, anybody know like any tricks that you could play to actually do better than what XV6 does?
I guess maybe if you had some transactions that you could abort.
Yeah, I guess you have transactions. If all system calls executed in a transaction, you could abort the transaction. In some ways, you think like so Linux, for example, does something like that. Although there's no notion of transaction, what it tries to do, it will basically it will clean up whatever state it has. It will remember like it's a kernel thread somewhere deep. It will try to clean up, unwind its stack, unwind any resources that might actually be happening. Go back to the beginning of the kernel, or like where the system call happened, and then re-execute the system call. Right? And now, then the second re-execution will notice, I'm killed, so I got to go and return it back to user space. But that unwinding is actually pretty tricky to get right, and there are corner cases where often, it is not right. This is one of the trickiest parts of any sort of kernel that you can look at. Yeah.
What happens when on recursive interrupts? Are we guaranteed that at the end of trap we're actually returning it to user space and not just handling the recursive interrupt?
I mean, even if we executed a recursive interrupt, that'd be perfectly fine, right? Because we're sitting on the kernel stack. The kernel that process might be about to return to user space. If we get an interrupt before we run to user space, we'll deal with the interrupt. We'll run for a short period of time. Interrupt will return. And we'll return back on the stack, and then we'll try to return to user space, and then we'll kill it.
But what if the current execution of trap is 2 interrupts deep in the interrupt stack?
No, it can't be traced, right? The trap always sits at the top of the interrupt stack, not at the at the bottom or in between any interrupt handlers. Because you came from user space onto the stack, and the first thing you do is like at the top of the stack, you take the trap call, the system call. So you can never have a trap frame in the middle of 2 interrupt frames. It's just not possible, the way things are set up. Okay, now, so basically getting killed actually right in the interaction between sleep and kill is very, very complicated. And in fact, and so we're seeing basically that a process can be delayed for a long, long time. And in fact, to be completely honest, in XV6, a process can be delayed, killed infinitely long. That's not completely desirable, but let me show you a case and why that can happen. In fact, it's the same piece of code that we already looked at. So how would it be possible that, for example, a thread that actually is sitting in the reading from the standard input in this particular sequence of code that actually will never, never return, nor get cleaned up? Yeah, there's no input, certainly that will generate, so there's no input, but it gets killed. Will it actually return to user space with -1, or is that guaranteed that that will happen? Right. Despite there being locks, and there's only 6 lines of code, there's a race condition here. Right? Anybody can pick out the race condition? Yeah.
like let's say you acquire the input lock and then you're marked as killed.
Mm-hmm.
Would that potentially cause problems?
Well, you're in the right. Clearly it has to do something with p-kill, correct? How could this? So there are two. How can we get a raise here? So there's one thread doing kill, and there's one other thread doing console read. And let's say the following sequence happens, right? The guy just came out of sleep for some other reason. It goes back, it checks p-kill. Let's say p-kill was not set yet, right? Because this thread actually just got at the start of the kill function, but it hasn't set p-kill yet. And now, before actually console read calls sleep, right? Just between here, this kill function runs and actually sets p-kill to 1. It says p-kill to 1, it will run, correct, and we'll do a wake up for anybody that's sleeping. And that's we'll look at for the target process in the proc table. We'll see if the target process is sleeping. If it's not sleeping, then it won't do anything. If it was sleeping, it will do wake up. It's not sleeping, correct, because it hasn't gone to sleep yet. And so it does nothing and returns, correct, kill. And now right now, this process actually is going to call sleep and actually go to sleep. Correct.
Can we modify sleep to check p-killed and just make it return if the process?
Yeah, we could modify sleep to check for p-kill, and then that would be solve part of the problem. And so we'll make sure, one way to think about it, just yet another optimization to make sure that the target process actually gets killed quite a little bit quicker, correct? In general, of course, this process will get killed at some point, right? Because when the next time the user types input, then we'll get an interrupt and then we'll be woken up. But it could be in this particular scenario, it could be the case the user never types input anymore at all. Isn't it very important that the process actually gets killed? Probably not, right? And so we chose not to do anything about this case. You could imagine actually putting a p-kill check in, and then that doesn't guarantee that you get all the cases. You still have a long delay before you get killed. Does that make sense? Any questions about this? So okay, so the key way basically that x86 get out of it is changing this or stating what the spec of kill is, namely kill means you will never run the user instruction again, but you might run for a long time in the kernel. Okay? Any questions further about this? Okay, good. So then this is the last lecture on this sort of process and threads and all that stuff. So hopefully we're completely clear on this topic now. You will, for the homework, you will implement another primitive for conditional synchronization called barriers, where you allow a number of threads to wait until they enter all the barriers before you let them proceed. You get to implement that using sleep and condition variables, which is a form of sleep and wake up, and it introduces a couple of interesting synchronization problems. It's a classic concurrency challenge problem. All right, good luck. See you Monday.